Hello, everyone. Good morning. I have the advantage of being on Eastern time, so it's getting close to afternoon for me. Yeah, I'm Jared Siegel. I'm a second-year grad student at Princeton, and today I'm going to be discussing some new methods for stellar activity mitigation, with an emphasis on how to keep things physically motivated. The work I'm presenting today is the culmination of several projects with many wonderful groups of collaborators, a condensed list of which is shown here. So to begin, here we have solar dynamics orbiter images, sun and H alpha, and then below are the corresponding radial velocities from the Harp's North spectrograph. Now here, of course, all planetary motion has been taken out. So these are truly anomalous radial velocities, all originating from stellar activity on or near the solar surface. And what's particularly scary for exoplanet science is that when this graphic was made around 3 years ago now, the sun was in a particularly quiet phase. Yet we still have well over a meter per second of residuals in our radial velocity time series. And not only that, but our residuals are highly time correlated. Now, all the complexity in the figure we're just looking at can really be broken down to three main types of physical processes. We, of course, have surface features like spots and plages. For many solar type stars, these are going to be the dominant source of stellar activity. As stars rotate, these surface features move across their surfaces and can thus induce quasi-sinusoidal rate of velocity variation with a characteristic period equal to the star's rotation rate. We then also have granulation, rising and falling convective cells. This itself is going to create a net convective blueshift. For the sun, this is on the order of 600 meters per second. But we can also get time variation from this because the cells are rising and falling stochastically with respect to each other. There are then also pressure modes oscillating in the outer layers of our stars. Each of these has its own characteristic timescale, and this really spells doom for any simple attempt to detrend the stellar activity. We have multiple physical processes taking place, each at their own timescales, and even more terrifying, each of these timescales is also varying as a function of time. Today, I'm largely going to be focusing on spots and plages. These can often be grouped together into what's known as rotation modulation. There's a couple of reasons to focus on these first. I think the simplest is really just that by being tied to the rotation of their host stars, these signals often can look sinusoidal and a lot like the Keplerian signals that we're trying to actually study. Towards the end of my talk today, I'm going to make a slight interlude into pressure modes as one of the science cases for a lot of the new methods we're trying to develop. But of course, I am by no means the first one to ever think about stellar activity in the complex of exoplanets. And as a result, I think it's important to kind of cover the landscape before we go too far. There are, of course, things like activity indicators, such as calcium H and K, or the full width half max of the cross correlation function. These can then be used to either train complex models or just for simple linear detrending. There have then also been many attempts to try to take into account the geometry of spots and other surface features on stars, and then simply create geometric models for how they should behave. These models are great because they're physically motivated, so they're far more constrained. However, they often require that we have high cadence, essentially to do something like take a first time derivative, or really just have the stellar rotation rate well visually resolved. There are also then more data-driven methods, such as Gaussian processes and machine learning, which are now really becoming the workhorse of activity these days. But of course, these are notoriously flexible by their very nature. And so I think it's important before I go too far and tell you about all the new methods we're developing, just to first try to motivate where we want to add ourselves onto a graphic like this. And the first thing we're trying to emphasize is physically motivated models. Now, this doesn't mean we want to toss out everything data-driven, but it instead means we want to have a counterbalance, that when we have a very flexible model, we can run soundness checks. Let's make sure that our more constrained physically motivated models give us similar answers. Not only that, but physically motivated models are essentially a really nice dynamo. We run a physically motivated model. It tells us about how the stellar activity is behaving while we're also doing our mitigation. And we can take that to learn a lot about stellar activity. We can then develop our next generation of model, and on we go. But of course, another thing I really want to emphasize is that our models have to be accessible. We want things that run on our standard data products, things like the cross correlation function or the 1D spectrum. We also want things that can operate on realistic observing cases. Standard stars are great, but they're certainly the minority of our exoplanet cases. So we want things that can operate on a wide range of cadences. So how can we actually do all these things? The first thing we're going to do is introduce the line-by-line methodology. This is really going to be our toolkit for today. After that, I'm going to kind of discuss one of the many applications of line-by-line, specifically this new physically motivated model for tackling rotation modulation. It's really just a revisiting of the kind of simplified spot model that's often known as FF prime. And then towards the end, I'm going to discuss several ongoing projects and where we want to go next. So to begin with kind of the line-by-line methodology, we can kind of just first consider a stellar spectrum such as this. And what the line-by-line methods are going to do, as the name would imply, is calculate the radial velocity for each of these spectral lines independently. It's going to give you a very large data set at the end of the day. But of course, that's not how we typically measure radial velocities. Instead, we're much more used to doing something like this, comparing our observed spectrum to a template where we believe the spectral lines to be in our own rest frame. We then just slide this template back and forth in velocity space in order to create a cross-correlation function. And when we do this, we are inherently taking a spectrum averaged radial velocity. And there's a couple reasons that this is actually a good thing to do for exoplanet science. For one, we know Keplerian signals are going to affect our entire wavelength range uniformly. That's just how it's going to work, which means that taking all of our spectral range together makes sense. But of course, 1 meter per second, let alone 10 centimeters per second, these are really small signals that we're trying to find. So using as many photons as possible is still a good idea. The reason that these arguments break down and the reason line-by-line toolkits are valuable to have is stellar activity. Stellar activity is not going to affect our entire wavelength range in the same way. Some lines are going to be more magnetically sensitive, others are going to be more probes of the chromosphere. And we kind of already know this intuitively by the fact that we have activity indicators. So that's one reason we want a line-by-line toolkit, is we no longer want to average over all of this varied behavior. We instead want to use it to start learning about stellar activity and start mitigating all of its processes. Another reason is instrument systematics. If you have that pesky yearly signal in your radial velocity data set, line by line is a great way to determine if it's coming from the entire wavelength range, if it's chromatic, if it's coming from your CCD stitchings, if it's coming from the edges of your orders. Just having this toolkit available really can speed up a lot of these instrumentation challenges. So that's why you would want line by line. What does the actual recipe look like? The current recipe is still largely coming from the kind of initial paper from Demuse 18. And the general idea is that you'll take your stellar spectrum and you'll just first define all the spectral lines you want to study. Here I'm doing this via simple local mins and maxes heuristic formula, but you could also do this by comparing to known line lists, say from your cross-correlation functions. You'll then want to try to toss out all the spectral lines that you think are just going to be too noisy to bother with. In this case, I'm just doing a minimum depth requirement and a minimum width requirement. But of course, there have been many papers since that have tried to really add a lot of complexity to these processes, looking into things like, should we even care about blended lines, how asymmetric lines change this picture, and so on. For today, I'm going to stick to the simplest implementation of line by line possible, largely to keep things as reproducible for everyone online today. But of course, if you have questions about these more complex methods, I'm happy to take those. So we've identified all of our spectral lines, and we're now just going to zoom in to a single one for one observation. So that observation is shown here in black. And you can see I'm comparing it to this smooth reference spectrum in gray. That reference spectrum is created by simply co-adding together all of the observations we have for this target. That creates an incredibly high signal stellar spectrum. And we can then just compare our observation to the reference to calculate a radial velocity via the template matching formula. Template matching is really just a least squares regression where we're solving for the radial velocity offset between our observed spectral line and the reference. I think it's important to note here as well that we've never made any assumption about what shape the spectral line has, or even that's a spectral line. This formula works just as well on a blend or a wing of a line or anything else. It's just generally easier to think in terms of spectral features. Of course, we're going to want to do more than just measure radial velocities, especially when it comes to activity studies. We might also be interested in how the spectral line's shape is changing. In general, that's easiest to measure in terms of depth variations. But if you're ambitious, you can also imagine doing things like width changes, asymmetry changes, and so on. So we've done this for all of our spectral lines. We've measured all the radial velocities. And if we now want to have our spectrum average radial velocity, this is essentially the measurement that's analogous to what we would get from a cross-correlation function. We'll simply take the weighted average across all of our spectral lines. So does it work? At this point in the talk, I sincerely hope so, but we might as well check. Here we're looking at one of the NEWID GTO targets. It's a relatively solar-type star in a moderately active state. You can see in the data reduction pipeline radial velocities. So these are all coming from a cross-correlation function. We can see that over this around 80 to 100-day baseline, we have quite strong activity. It's a clearly sinusoidal signal. When we compare it to our weighted average line-by-line radial velocities, we see a very nice agreement. Now, this, of course, is for one star, but the exact same types of comparisons have taken place across a wide range of spectral types by many different groups at this point. And again, this agreement shouldn't be particularly surprising, since template matching is really probing the same information as the cross-correlation function. But of course, just reproducing what we could already do is not the best thing for our users of time. So instead, let's focus a bit on what line-by-line can do that's different. In particular, we're going to zoom in to one spectral line here. This is a quite deep, high signal spectral line. And in fact, if we look at the radial velocity time series we get from this spectral line, we see that its error bars are on the order of 5 to 10 meters per second, which is quite good for one single spectral line. And even by eye, we can try to pick out that bulk activity signal we were just looking at on the last slide. In fact, one of the first tests you might want to run is to take this time series you just calculated for one spectral line and compare it to the spectrum averaged signal. And in this case, we can see we've identified a very activity-sensitive spectral line. But of course, we have many thousands of spectral lines that we're trying to study, so we can summarize all of these different ways of correlating in a plot such as this. So on the x-axis, we're plotting each line's mean radial velocity uncertainty, and the y-axis is the correlation between a line's radial velocity time series and the bulk radial velocity signal. And in this case, we have a quite simple story. As lines become higher signal, so that means we're moving to the left on the plot, we see that their correlation with the bulk signal increases. But of course, we're averaging over a lot of information in plots like this. For one, correlation is not the whole story. We're also interested in the amplitude of radial velocity perturbations, things like phase offsets, and so on. Not only that, but we also care about how all of this depends on the spectral line's parameters. So in this case, I've color-coded the exact same plot by wavelength, and we can also imagine doing this by depth. So these plots are not meant to show you all that you could do with line by line, but rather just to demonstrate how much information we have available to us. To really emphasize that point, we can do this correlation game on more than just line-by-line radial velocities. We can also consider more activity-centric observables, such as depth variations. So the plot on the right, the y-axis is now showing how correlated each line's individual depth variations are with the bulk activity signal. And then on the x-axis, we're plotting how accurately we were able to measure that line's depth variation. And you can see we might naively think we've just identified a large set of potential activity indicators. We've identified several dozen spectral lines where their depth variations are highly correlated with the activity signal of the star. This is the exact same thing that we're doing with something like calcium H and K. But of course, before we get too excited and start diving into all these spectral lines we've identified, it's also important to remember that the line-by-line data sets are inherently quite noisy. Each spectral line is probing somewhere between 10 and 20 pixels, meaning that our radial velocity error bars are at best going to be on the order of 5 to 10 meters per second. So white noise can potentially make things look correlated even if they're not. So it's important to run tests to check for that. There are many ways of doing this, but one of the simplest is just to redo your whole correlation analysis, but now with your radial velocity time series are just draws from a white noise process. In the 1st to 99th percentiles of the correlations you get back on that are shown here in the shaded purple regions. Now, for a bright star like the one we're looking at, with a very strong activity signal and many observations, we can actually see that the width of this white noise region is very small. This is telling us that we can actually start believing a lot of the trends we're seeing on these plots. But that's not always a guarantee, so it's important to still think about tests like this in more general cases. So now that we believe that we've actually identified activity-sensitive spectral lines, we can take all those spectral lines where their depth variations are correlated with the bulk activity signal, and we can just co-add them together. The idea being that if one activity indicator is good, dozens must be better. So that's done so here. And you can see that just by eye, we've made a really nice reproduction of the bulk activity signal in this relatively simple data-driven approach. And this is something we introduced now a year ago. So hopefully, by this point, I've convinced you that line-by-line data sets are very information-rich. But of course, what I showed is really just the tip of the iceberg. There's a lot more complex tests that we can start running when we have these large data sets. Things like PCA analysis, machine learning, these all start opening up to us when we take a line-by-line approach. But of course, I did promise earlier on as well that we really want to stay physically motivated. So before we get too excited about all the fun data science things we can do with these new data products, let's also ask, why are spectral lines behaving differently from each other? And one of the simplest answers is that different spectral lines are going to respond differently to magnetic field changes. Just to kind of highlight what those changes can look like, here I'm showing the results of MHD simulations of granulation from Siegel 2013. The green and purple line profiles are coming from regions in the simulation with relatively weak magnetic field strength. However, the blue and red line profiles are coming from regions with very strong magnetic field strength. And you can see that Zeeman splitting has drastically changed the line morphology. Now, this, of course, is one case, and there's quite a large cottage industry being built up of folks taking plasma boxes and just studying how the shape of a spectral line is dependent on changing plasma conditions. So that's one reason spectral lines will behave differently due to stellar activity. But another one is that shallow spectral lines and deeper spectral lines are going to be sensitive to different parts of the photosphere purely just by opacity. We can zoom in on what we mean by that. If we consider a simplified line profile, or equivalently just a cross-correlation function as I plotted it here, when you're in the wings, you've on average seen far less absorption than when you're looking into the core. So that means that the wings of our spectral line, or equivalently the wings of our cross-correlation function, are probing deeper into the stellar atmosphere. And this means we're probing hotter temperatures. Analogously, if we're looking in the core of our spectral line, we're going to be more biased towards looking higher in the stellar atmosphere and cooler temperatures. And this whole argument is really just a statement that optical depth and temperature both decrease in a simplified photosphere model as a function of radius. This, again, is just a statement about opacities. However, there's a lot of exciting things that can start happening when you make this connection to stellar activity. And this was recently pointed out by Kaldamula's 2022 paper. So we can zoom in on what we mean by that. In particular, I've been quite qualitative so far, just talking abstractly about temperature formations. But what do we mean? So we're going to first need a stellar atmosphere model. This, again, is just a 1D plane parallel atmosphere model, and we're just going to feed it up with all of our spectral lines in the relevant atomic parameters. Then at any given wavelength, we can calculate the contribution function. This is saying, as a function of temperature, what is the cumulative distribution of flux? So for instance, I can define temperature, the formation temperature, as the point at which I know 50% of my flux is coming from cooler temperatures and 50% of my flux is coming from higher temperatures. Folks may be more used to seeing this, the contribution function, in terms of optical depth. But again, when you're in a photosphere, where you know optical depth and temperature both monotonically decrease with radius, this is a relatively straightforward change of variables. Now, this, of course, is just for one wavelength, but we can repeat this process for an entire synthetic spectrum to create something like this. And again, many thanks to Colin for sharing this data with me. On the x-axis, we just have wavelength. And on the y-axis, we have the calculated temperature formation. And what we'll notice here is that line depth is actually a wonderful proxy of the temperature formation. And this is what I was mentioning before. And this is really just a statement that long-term changes in opacity due to wavelength are happening relatively slowly on stellar atmospheres. So that's, a lot of deep diving into atmosphere talk, but what does it mean for line by line? What it really means is that if I'm looking at a shallow spectral line, I am on average probing hotter temperatures in the photosphere than if I'm looking at a deep spectral line. And that means that if I see chain differences in stellar activity behavior of shallow and deep spectral lines, I am more likely than not actually just probing differences in stellar activity as a function of depth in the stellar atmosphere. So that concludes our kind of mini tutorial on line by line radial velocities, as well as kind of then a detour to kind of all of the reasons why we actually expect spectral lines to behave differently. What we're going to do now is take all of that, kind of condense it together into one specific application. In particular, we're going to try to address rotation modulation. So as I mentioned before, rotation modulation arises from spots and plages on the stellar surface. As stars then rotate, this can create quasi-sinusoidal signals in our data set that can often look quite a lot like Keplerian signals. So we're going to try to take all of these complexities and just simplify it down into something we can model. And in particular, spots and plages can really be broken down into two main types of radial velocity perturbations that we then measure: the rotation perturbation and the convection perturbation. So what do I mean by that? Well, let's take a look at what a star would look like through the lens of radial velocities. To do so, we're going to create some cartoons where our star's spin axis is going to be straight up. That then means that the blue shifted hemisphere is coming towards us, and the red shifted hemisphere is going away from us, just like shown in the cartoon here. If I then place a spot on this star, it's going to create an imbalance between the red and blue shifted hemispheres, which will then create a net radial velocity signal. And thankfully, if we put aside different rotation for a second, we can express what this radial velocity perturbation would be simply as a function of the spot's longitude and latitude. Of course, there's more going on stars than just rotation. There is also convective blueshift. When I place a plage on a stellar surface, it will locally suppress the convective blueshift. This will then create a radial velocity perturbation, again, just as a function of the spot's longitude and latitude. We can actually plot up what that would look like. We're going to just place a spot at the equator, and then have the star rotate. We're now looking at the convective perturbation in purple and the rotation perturbation in green. To make things clear, the diagram in the upper right corner here is showing the location of the spot at that specific rotation phase. To clarify things even more, we can add another one on the left-hand side. And to clarify things even more, we can add eyebrows. I really like that joke. Okay, so that's the rotation convection and how it can be broken down into just functions of longitude and latitude. But of course, longitude and latitude are not the most easy to infer or even observe quantities. And what is much easier to observe, or at least approximate, is stellar flux. And that's what was done in the FFPI model. It was essentially saying that if we take all of the math behind the rotation and convection perturbations, we can notice that the flux perturbations have a very similar functional form, and we can simply then rewrite these perturbations all in terms of flux. And that's great for us because flux can either be just observed via a photometry campaign, or it can be approximated with something like H alpha. However, as we'll notice here, for our rotation perturbation, we are required to take a first time derivative. This can be quite a pesky problem for us because it really means we have to have incredibly high observing cadence in order to do that well. But can we now try to revisit this model using what we know about formation temperature and all of the line-by-line toolkits we just discussed? Thankfully, the answer is yes. So again, just for a refresher, we'll consider here our simplified line profile. The wings of the spectral line are, again, on average, going to be probing higher temperatures of formation because they've seen less absorption, whereas the cores of our spectral lines will be probing cooler temperatures, so essentially higher in the stellar atmosphere. And it has been empirically shown, for these studies here, as well as several others prior, that if you isolate the tops of spectral lines, or equivalently, if you look at only shallow spectral lines, that the radial velocity signal you get back is far more correlated with the convective perturbation. It's been shown to a lesser extent that if you identify the bottoms of your spectral lines, or equivalently the deepest spectral lines, that you are now more correlated with the rotation perturbation. So we can use that to our advantage. What we're going to do is imagine a simplified case where our radial velocity signal is simply a combination of the rotation, the convection, the Keplerian signals. For all of the little bit of algebra I'm about to do, I promise the orange symbols will refer to observables. So that's something we measure. And the black symbols are things we're trying to infer and actually study. So what we're going to do is introduce two radial velocity time series. One calculated using the tops of spectral lines, and the other calculated using the bottoms of spectral lines, or equivalently using the tops and bottoms of the cross-correlation function, or also just using shallow and deep spectral lines. All we care about is the fact that RV1 and RV2 just have different contributions from the rotation and convection perturbations. Because what that means is if we just simply take the difference of them, the Keplerian signal will fall away because it's going to affect all wavelengths equally. And this just leaves us with a linear combination of the rotation and convection perturbations. Again, I promise we're almost done with the math. Some of you will notice that this is similar just to the bisector inverse slope. When we plug this then back in to the rotation and convection perturbations, we end up with this simplified functional form at the bottom. What we've been able to do, though, is get rid of that need for a first-time derivative by substituting in these new radial velocity observables. One calculated using the tops of our spectral lines, the other calculated using the bottom. A similar form appeared in Rajpal 2015 as well, although we're using it in a quite different way. So this is going to be our model. What we've done is we've taken the F of prime and just rewritten it using our knowledge about formation temperature. So does it work? Again, at this point, I sincerely hope so. So to make things as accessible as possible, here I'm going to be using cross-correlation function radial velocities. As we'll see on the next slide, we can do the exact same thing with line by line, but for the new solar data, all the cross-correlation function radial velocities are publicly available. So hopefully these plots can be reproduced quite easily. Here I'm showing the binned radial velocities for the solar data, and here is our model. So we see we have a really nice agreement. We're detrending down to around the meter per second level, which is what we would expect from a combination of P modes and granulation, particularly since we're not trying to bin them in any sophisticated way. And the ingredients to this model, it's worth pointing out, are just a flux proxy and our two new radial velocity time series. One calculated using the upper 40% of this cross-correlation function, and the other calculated using the bottom 40% of the cross-correlation function. Now, this was all using the cross-correlation function. As I've said, we can do the exact same thing in a line-by-line setting. That's now the top left panel here. And you see the model in RV comparison is equally strong no matter what method we're using. For a bit more background, the center columns are now showing one of the ingredients. So this is the difference in the RVs using either the tops of our spectral lines or the bottom of our spectral lines. And on the far right, we're showing our flux proxy. So this is depth variations, either the cross-correlation function or individual spectral lines. So thus far, we've been able to say that we can take the simplified spot model, we can rewrite it in a way where we no longer have to take a derivative. So it's now considerably more accessible. But we also were promising for quite some time that everything is going to be physically driven. In order to prove that our model is actually, tying itself back to the physics of stellar activity, one thing that we want to be able to do is independently recover the convection and rotation perturbations. We can actually do that. Here, just to kind of get an answer from the back of the book for comparison, These are the radial velocities for the convection and rotation perturbations inferred by the Solar Dynamics Observatory. So you have these spatially resolved images, the sun. You can then identify which pixels are associated with spots and plages in order to then calculate the convective and rotation perturbations. In our models, predictions are shown here. So what's exciting is that we're not only reproducing the bulk activity signal, we've correctly separated out the convection and the rotation perturbations. And this is opening a lot of doors for us. To our knowledge, this has not really been done before, and this is all happening using easily accessible radial velocity data products, things like a one-dimensional spectrum or the cross-correlation function. To really drive home the point, again, on the left-hand side, we are looking at the convective perturbation, and on the right-hand side, we're looking at the rotation perturbation. So that was all for the sun, which is naturally an incredibly high signal case where we have very high cadence. So just to make sure that we have done something that's a bit more general and accessible, let's return to our standard star that we were looking at in the line-by-line tutorials. Here we can see our activity signal is again quite strong, and our model prediction is shown in blue. And we're bringing down again the final radial velocity RMS to around the meter per second level. And again, because we're only here trying to tackle rotation modulation, that's around the level we would expect. We can again make our predictions, what we believe the independent underlying components are, the convective perturbation and the rotation perturbation. Unfortunately, in this case, we don't have SDO orbiting the star, so we cannot easily check the back of the book to see an independent prediction for these perturbations. However, hopefully, Rachel Rottenbacher's work on interferometry of stellar surfaces might make that possible in the future. So again, to summarize, we took our simplified spot model, we combined it together with formation temperature in order to rewrite it for two main benefits. The first is that we got rid of the need for incredibly high cadence. And the second, we've now explicitly mapped our model to observables, things like the convective perturbation, the rotation perturbation. And hopefully, the folks who really only care about planets are excited because we found a way to make the FF prime model applicable to a whole bunch more systems where maybe our cadence was too low to take that first time derivative. But also the stellar astrophysics folks should be excited because we're now, really mapping and probing these things in the stellar atmosphere. But how much farther can we push it? Well, earlier I mentioned that folks had seen that if you take shallow spectral lines, or equivalently, just the wings of spectral lines, that the radial velocity time series calculated was more strongly correlated with the convective activity signal. And it was also seen to a lesser extent that if you look at the bottoms of spectral lines, or equivalently deep spectral lines, that there was a stronger correlation with the rotation perturbation. So can we actually see that again? And can we perhaps even map that out as a function of line depth? And thankfully we can. The free parameters of our model are telling us two things. We give it two radial velocity time series. Again, one calculated using an upper portion of the line profile, another calculated using the bottom portion of the line profile. And the free parameters are just telling us what is the difference in amplitude of the rotation and convection perturbations. So for instance, if we consider two slices of the line profile that are very close together, we see that the return coefficients are near zero. Again, generally makes sense. We've said that if we pick two parts of the line profile that are very close together, their radial velocity components have almost equal contributions with respect to each other of the convection and rotation signals. But of course, if we now compare the bottom of the spectral line with radial velocities calculated slightly higher up in the line profile, we now see that the rotation perturbation is considerably stronger in the bottom of the spectral line, and that the convection perturbation is considerably stronger the higher up we go. And we can repeat this process over and over until we've now mapped out as a function of line depth, position, the convection and the rotation perturbations. Again, this is something we're really excited about. But that was just for the sun. We can repeat this process for our standard star as well. And we see we get the same lesson. And again, seen before, that when you're looking at the tops of spectral lines, we are now seeing that you're more sensitive to the convective perturbation, whereas the bottoms are more sensitive to the rotation perturbation. But what's new and exciting is we're actually mapping this out as a function of position in the spectral line. Or some may also remember from several slides ago now that I showed that if you use, stellar atmosphere modeling, so you create a 1D plane parallel atmosphere, you can actually try to calculate what these temperatures of formation are, instead of just having to talk about them in terms of scaling relations. So what that means is we can take the bins we just had in terms of line depth, and we can convert them into a mean formation temperature. So here we're looking at the sun. On the x-axis, we now just have that mean temperature. What we've done is we've now mapped out the strength of the rotation perturbation and the strength of the convective perturbation as a function of temperature, which again, in something like the photosphere where the temperature to radius relationship is relatively straightforward, this just means that we can literally watch as we probe deeper into the atmosphere how the dependence on these two perturbations is changing. And again, this is exciting if you're interested in stellar atmospheres, but this is also opening up a whole new set of observables and training data sets for folks who are interested in creating more data-driven models for stellar activity mitigation. So that concludes our trip into rotation modulation. Everything I just described, we've been giving the bulk, very generic name of the rotation-convection model. And again, the general idea is that we can take this simplified spot model that's for a long time been used in the FF prime universe. We can just combine it with formation temperature to do all the wonderful things that we've just shown here. In particular, we get great detrending. But we are also able to do a lot of interesting physics. We're recovering the underlying components of the stellar activity signal just using cross-correlation functions or a 1D spectrum. So that's great, but we're not satisfied. We want to do more. So where are we heading now? So the first place we're turning to is P-modes. This is a project being led by Princeton Junior Vivek. This was his summer project this last year. He's great, everyone hire him. This project's being led by Ashley Shantos, postdoc here. And the idea is actually to play very similar games that we are with the rotation modulation side of things, but now turning towards P-modes. So here's their primary data set. It's 1 day, relatively clean day, from the NEWID solar data set. And they're hoping to now extend this to several months, but of course it increases run times for them. And if you zoom in here to around an hour, we can by eye pick out around this 5-minute period P-mode oscillations. But of course, if you had something like KPF, which will hopefully be getting around a minute cadence on its solar observations, a plot like this becomes even more interesting. Here, the radial velocities are calculated using the entire spectral range. But of course, we can repeat the process, now only calculating the radial velocities using the bottom portions of our spectral lines. And we can do it again, now calculating the radial velocities only using the tops of our spectral lines. On a plot like this, it's really hard to see if we've done anything interesting or just added noise. So Vivek's been doing a lot of hard work and taking all that information and putting it into frequency space. The frequency periodogram from the bulk radial velocity signal is shown in black. And the periodogram from the lower 40% of the line profiles is on the left, and that from the upper 40% is on the right. Now, of course, each of these is going to have their own noise profiles. So a lot of work's going into making sure we understand if any of these frequency changes are significant. However, folks inside the group are very optimistic that we are probing some interesting physics. Because again, what we're doing here is when we go from the upper 40% of the line profiles that is deeper in the atmosphere on average, the lower 40% is going to be higher in the atmosphere. So we're now mapping out the P-mode period distribution as a function of depth inside of the stellar atmosphere. Now, again, this is a planet talk, so I thought I should also spend some time chatting about, how we're actually trying to take all of these line-by-line methods and use them on systems where we're trying to recover planets instead of just study activity. So again, for doing that, I'm going to focus on TOI 700. This is a really exciting test system, which for a long time had one Earth-sized habitable zone planet. But now in pink, you can see a new one's been discovered just interior to that. And for now, we have 2 semesters of espresso data. All of this is being led by the wonderful Emily Gilbert and many other RV collaborators. These RVs in the top panels here are from the espresso data reduction pipeline. You can see they're a little bit noisy. If we take the line-by-line toolkit I was describing before, we get the green points here. So we see we've cut out quite a bit of the white noise. And all the line-by-line data set's doing here is just trying to identify deep, well-isolated spectral lines that will have a lot of information content. And again, on an M-dwarf, that's not the easiest game to play. We also see we have pretty nice agreement with the SBART code as well. That's another template matching Bayesian approach. And on the bottom here, you can see we have the period distributions from all of these radial velocities. The planet signals are now shown in black. So these are from the test periods. And the stellar activity signal and its 1/2 alias are shown in red. And you can see we got a little unlucky here that the stellar activity signal is right where we want to be studying all these interesting planet frequencies. So this is a star where stellar activity mitigation is of the utmost importance. I think it also drives home the case that you can't always just limit yourself to studying quiet stars, because sometimes the most interesting systems are just going to be around loud stars. So here are the results from a GP trained on the rotation period, as well as the full width half max. These are using the SBART radial velocities for now, and hopefully in the next few days, once I find a minute or two, we'll repeat the process using line-by-line radial velocities. For now, there are strong mass recoveries for 2 of the planets. But again, I did emphasize that this is all being done using GPs. And I just gave around 15 minutes before, going on and on about how we want things to be physically motivated and how we can try to tackle rotation modulation using all these new tools. And the real challenge for us right now is that this star is one of the lowest signal to noise we've tried to look at yet. The brightest, highest orders right now are around a signal to noise of 60. For reference, the sun's around 400, and most of the GTO targets we look at are well above 100 in terms of signal to noise. So a lot of interesting stuff's going on right now, trying to see how we can push our methods to this lower signal to noise regime. And with that, I'll briefly cover my conclusions. Hopefully the thing you took from the first part of the talk is that line-by-line RVs are great. And even if you are only interested in instrument systematics, they can still be very valuable to you. But again, the reason line-by-line RVs are advantageous is really just this idea that stellar activity does not affect all spectral lines in the same way. So when we average over all that information, we're losing a lot of ability to start studying these processes. I then introduced this rotation-convection model, this new way of trying to tackle rotation modulation by combining the spot model from FF prime with a lot of ideas about formation temperature. And we saw that we had 3 main benefits. The first really is this point I've been harping on the whole talk about accessibility. This can run completely just using the cross-correlation functions or the 1D spectrum. It also got rid of that first derivative requirement, so we can now operate at a wide range of observing cadences. But lastly, and most exciting to me at least, it's physically motivated. So we were able to do things like get great detrending, but we were also able to recover the underlying components. We saw what the convective perturbation was. We confirmed it matched independent observations. We were even then able to map how all of these different components change as a function of depth within the sun. And with that, I'll open up to questions. Thank you all for your time.
Wonderful. Thank you so much for an excellent talk, Jared. I invite folks to use the little clapping hands emoji to show your appreciation. And as Jared said, let's open up the floor to questions. Please feel free to raise your hand in Zoom, and I'll call on folks as hands show up. I will take host prerogative and ask the first one. So Jared, you mentioned that with the TOI 700 system, it's a lower signal to noise case than certainly the sun or even HD 26965. Do you think there's a floor, whereas we're looking either at fainter stars or using more moderately sized telescopes than the VLT, where line by line just comes up against a wall and isn't something you could employ? Or do you think there are benefits even if there are less signal in the individual lines?
Yeah, I think that's an important question. I can say I've tried to carve out the space of using the simplest line-by-line implementations possible. So for instance, I mentioned, I'm trying to do only like filtering lines based off depth and things like that. So I definitely think as you're more sophisticated in terms of your line selection criteria, you can push towards lower signals. But I think the kind of saving grace here is really going to be, we have a lot of bright M-dwarfs just lying around. We can study them, identify the best spectral lines there, So then when we go to these lower signal targets, we essentially have a prior on what we expect. We know which lines to look at beforehand. This is the kind of the same philosophy as looking at calcium H and K everywhere we go. We learned from the sun, it's a great indicator. So now when we look at other stars, we keep tracking that same spectral line.
Gotcha, thank you. Eric Ford, I see your hand up, go right ahead.
Yeah, so you may have said, but I missed it. When you use the F squared term flux, are you actually using some photometric flux or using some spectral proxy for it? How are you dealing with that for the sun, and if it's different for the sun and other stars?
Yeah, great question. Okay, so for today, everything I showed is using depth variations as a flux proxy. So when I showed cross-correlation plots, that was just literally changes in the cross-correlation function's depth. And for the line-by-line ones, that was the depth metric. The cool thing, though, is that just from examples with SOAP, we were able to be pretty convinced that using actual flux versus using this depth variation versus full width half max was certainly not our dominant systematic.
So for the CCF ones, you're using the depth of the CCF, but for the line by line, what were you using?
So we're tracking each line's individual change in depth variation, and then we're just grabbing the percentages where those variations are above the white noise limit. So all the ones where we have a significant change in variation.
Okay, so you're picking the lines whose depth you can measure well, and then using it. Okay, got it, thanks.
As we kind of saw earlier, it's essentially a higher signal version of what the cross-correlation function gave us. Yeah.
Good, thanks.
Other questions for Jared? While people ponder, can you talk a little bit? Oh, Heather, you go right ahead.
Yeah, I was wondering when you're doing your RV1 and your RV2, because you kind of showed that you explored different definitions of like top and bottom when you were looking at some of your later plots, when you're trying to explore like how things behave with like formation temperature and so on. But when you're actually trying to isolate like the rotation and the convective side of things, did you try doing something more than just saying the top 40% and the bottom 40%? Did you try like optimizing those at all?
Yeah, so for right now, choosing the top 40% and bottom 40% is what was used for kind of the main detrending plots. For the one where we're trying to actually map out the contributions, you can see we're making many different slices. And what's great, and I don't believe I have this in an extra slide, but I'm happy to kind of share it as well. The recovered components, so like the convective perturbation, the rotation perturbation, if you just overplot them for each of the different slice choices, they're almost identical. The only thing that's changing is really photon noise.
Okay, thanks.
Okay, other folks in the audience? Okay, I'll sneak my question in here while people ponder. So for folks who haven't yet gotten started using line-by-line velocities, Jared, can you talk a little bit about the overheads of producing that data set in case, and ways to go about that if folks want to try building that into their own analyses as they're working on stellar activity or planet conformations?
Yeah, of course. So for right now, if you wanted to reduce like a typical rate of velocity data set, so let's say 50 observations, that can be done on the order of 15 minutes. Most of the overhead there is really that I'm not a computer scientist. So I'm sure there are folks out there who can optimize even more. If you want to do a solar data set, so many thousands of spectra, that's when you start getting into cases where you need to run things for overnight. But for most cases we deal with, the run times are all within human lifetimes. I'll also say that we have all the documentation ready that the kind of line-by-line pipeline we're doing will hopefully be publicly released alongside the TOI 700 rate of velocity paper.
Wonderful, looking forward to it. Eric, I see your hand up again, go ahead.
So do you have a sense of how many lines you're using for the sun and some of the other stars?
So for the new spectrograph, it's a little trickier than usual because we have a lot of overlap between the orders. So for instance, on the sun, we naively identified 12,000 spectral lines. So yeah, that's a lot of information. Once you cut out things based off like signal to noise considerations and overlap, we end up with on the order of 3,000 unique spectral lines. That is kind of the typical number we get. It's pretty similar for express, especially we kind of the same number across the board. The only time that really changes is, of course, M dwarfs, because then even defining spectral lines becomes quite tricky. But for solar type stars, it's on the order of a couple thousand.
Cool. One interesting thing is, like we've done some work using much smaller line lists, 1,000 or several hundred. And so I'd be very curious that the interaction of like, if it would be easy to send you a subset line list and kind of see if that does better or worse.
Yeah, of course. Yeah, I think that'd be great.
Okay, last call for questions from the audience. Okay, I don't see any other hands popping up. Thank you again, Jared, for giving a wonderful presentation. Again, I invite the audience to clap your hands via the emojis. And yeah, we will return next month again on October 26th with Jacob Lund talking again about stellar variability related things, our favorite topic here in the land of EPRV. But hope you all stay well until then. Jared's recording will be posted to the EPRV RCN drive as per usual, and summer emails will go out probably tomorrow. So have a great rest of September, and I hope to see you all next month.